Hello, I'm Nathan Drenkow, and I'll be presenting our work, RobustCLEVR, a benchmark and framework for evaluating robustness in object-centric learning. The primary motivation behind our work is that as demand increases for the use of AI in safety and cost-critical applications, such as in healthcare or autonomous systems, we need vision algorithms which are robust to the variability in imaging conditions that arise across real-world domains and applications. Recent studies have shown that in spite of considerable research efforts and progress in deep learning for computer vision, deep neural networks remain brittle to naturally occurring imaging conditions, such as due to the environment or sensor. Additional studies have shown the propensity of deep neural networks to ignore task-relevant features and rely on textures or other shortcut features, which are spuriously associated with task labels. Object-centric learning has gained recent popularity and offers the potential to overcome some of these limitations. So the primary aim of object-centric learning is to perform explicit unsupervised scene parsing by forcing deep neural networks to extract per object representations, which encode properties of the objects such as size, location, and appearance information. Common object-centric approaches first encode an image as a set of vector representations or slots, each of which corresponds to a single object in the scene. Then a separate decoder learns to reconstruct the original image and generate object masks from these slot representations. The optimization is unsupervised such that the network cannot simply learn to associate shortcut features with specific object labels. As such, we ask whether the mechanisms required for performing this unsupervised object discovery are robust to naturally occurring imaging conditions and corruptions. In order to properly evaluate these object-centric methods, we first consider how to generate image data containing sufficiently challenging and realistic conditions. In contrast to the common corruptions framework, which pre-specifies categories of image corruptions for evaluation, we shift our focus to the factors of the imaging process and the interactions that contribute to complex distortions that are likely to arise in the wild. Such factors include properties of the environment, the sensor, and the post-processing pipeline. Knowledge of the imaging domain allows us to identify these factors and their potential interactions. For instance, in natural imagery, we know that the light levels in the environment will subsequently affect the choice of exposure time or aperture. To explicitly codify our assumptions about the image generating process, we specify a graphical causal model as a directed acyclic graph, which allows us to identify the relevant imaging factors and their interactions. Furthermore, we can then use the causal model to render images that capture these complex interactions. To do this, we implement the causal mechanisms which capture the functional relationship between each factor in the model and its direct parents. The causal model also induces a joint distribution over all factors, and values for those factors can be obtained by sampling from this distribution. To generate the image data, we use the causal model to first sample factor values, then following a topological ordering of the nodes in the model, we repeatedly apply the appropriate transformation to the base image and use the sampled factor value to parameterize each corresponding transformation. The structure of the DAG and the sampled factor values determine the nature and severity of the overall image distortion and enable substantial diversity of the rendered conditions. Our causal framework integrates seamlessly with the physics-based Blender rendering tool, and we use this then to generate several variants of the popular CLEVR dataset. Our framework enables the specification of arbitrary causal models, and we use this to generate the two contrasting variants shown here, one where the corruption factors are IID, and another where corruption factors are causally linked. While the image appearance varies significantly within and across the data sets from these two causal models, this may be difficult to qualitatively characterize, knowledge of the causal model and the sampled factor values provides a means for more in-depth interpretation of the resulting image data. We next perform the first known evaluation of the robustness of object-centric learning algorithms to naturalistic corruptions. We evaluate several high-performing baseline object-centric algorithms on multiple variants within our RobustCLEVR dataset. Each variant captures assumptions about the underlying data distribution and the train test conditions. Our results first show that, like other deep learning approaches, object-centric methods still exhibit sensitivity to challenging imaging conditions, and this presents new opportunities for future research to address the robustness performance gap. Furthermore, by assessing performance on image data generated from a range of causal models, we find that knowledge of the causal model also enables greater insight into differences in model performance. For example, large differences in performance are observed here for the noise corruption between the IID and non-IID settings. Here, knowledge of the causal model allows us to understand and identify that the lower performance in the non-IID case is driven by the influence of other upstream corruptions, which are absent in the IID setting. Overall, this work presents a novel framework for generating complex image distributions that can support downstream robustness evaluations. Our framework provides the means to achieve better alignment between evaluation datasets and expected deployment domains. And this is through the causal model approach, which allows us to maintain interpretability of the image distribution and image generating process while enabling evaluation of significantly more complex images than in the conventional common corruptions framework. We use our framework to generate the RobustCLEVR dataset and perform the first known evaluation of the robustness of object-centric learning algorithms to more realistic and challenging image conditions. While we find that object-centric methods are still brittle to small image corruptions, our framework provides a means to push future research forward to close the performance gap. If you'd like to learn more, please come visit us at our poster. Thank you.